Green now. Great. Yeah, so as Guy said, I started back in June last year. So unfortunately, that means although I've been uh, with you for a while now, I've unfortunately not got to meet many of you in person. So, but it's nice to be able to do this nonetheless, and hopefully I'll get to meet more of you over time. So my plan today is to talk about a lot of the background of what ozone depletion is and why it's important. And I'm hoping there's quite a sort of general, fairly broad audience here today. So I apologize to those of you who may already know a lot of this stuff, but to hopefully keep you a little bit entertained. Pandemic teaching has got me obsessed with Menti. So there's a Menti quiz, which there'll be a couple of questions as we go along. So you can go to this website, menti.com, and put in the code down here, and there'll be a couple of questions on that as I talk about the background. The code will stay in the bottom left-hand corner here, so don't worry about missing that. And then I'll try to get on a bit about some of my own research, although I won't go into too much of the weeds about that, but I'll talk a bit about the impact of Antarctic ozone depletion on the troposphere and how that is coupled to the Southern Ocean. And so my main kind of goal in talking to you as the GSI kind of community is to get across the fact that stratospheric ozone depletion is a really important environmental issue. I think sometimes it might be thought of as a kind of issue from the 1980s or 90s, but it's an important issue today, and so something relevant kind of within the GSI. And most importantly, anyone from all sorts of different backgrounds who might want to collaborate on issues around ozone and ozone depletion, please get in touch. Okay, so what is stratospheric ozone? So ozone is a gas which mostly exists in the lower stratosphere, so in this region between about 15 to 35 kilometers or so in altitude. This diagram may make it look like there's a lot of ozone in the atmosphere, but actually if we compress that column or that layer of ozone down to the surface, we'd end up with a layer of gas that's only about 3 millimeters thick. However, those 3 millimeters are very important. They absorb a large fraction of UV radiation. So specifically this UVB radiation, which is in the middle of the spectrum of UV radiation. So UVA reaches to the surface mostly, but that isn't too worrying and not too damaging. UVC is mostly absorbed by molecular oxygen above the ozone layer. The UVB is mostly absorbed by the ozone layer. The bit of UVB that does get to the surface is the kind of solar radiation that gives you sunburn, for instance. And so the importance of this thin layer of gas is highlighted in this quote that I put in the abstract for this talk from the citation for the 1995 Nobel Prize in Chemistry, which went to these 3 scientists who understood the chemistry that leads to ozone depletion. And this is saying that without this layer of ozone, life on the surface of Earth, on land at least, would be very difficult. It's also been identified as one of these 9 planetary boundaries that some of you may have heard about. This is a kind of concept of the things that are required for human life to be comfortable on Earth. And stratospheric ozone depletion is kind of identified as one of these, alongside things like fresh water and climate change and things. And you can see from this diagram, it's also been kind of identified as a area that's not too concerning. So this kind of green color here indicates we're kind of in a safe zone. And I'll try to argue that while that might be the case, it also doesn't mean we can be complacent about stratospheric ozone at the moment. There's also lots of links between stratospheric ozone and sustainable development goals. And I thought I'd mention this because I know that within the GSI, we've kind of organized ourselves or our research priorities within these UN Sustainable Development Goals. And if you go on the UN Environment Programme Ozone website, you can find this information page that kind of talks about how stratospheric ozone and is links with all these various goals around sustainable development. Okay, so how is ozone depleted in the atmosphere? Well, what happens is there are catalytic reactions which can occur where ozone is broken down into molecular oxygen in the atmosphere. And here are catalyst X in these chemical reactions. And I'm no chemist, so apologies for any chemistry mistakes I make here. And our catalysts are halogens, so things like chlorine and bromine. And they're emitted as part of ozone depleting substances, which most famous of which you've probably heard of are CFCs, chlorofluorocarbons. Sources of ozone depleting substances are things like spray cans, refrigerants in like air conditioning units or fridges and freezers. And another major source is in the blowing of insulation for in building. So this is what this is illustrating here. And the effect of this emission of our ozone depleting substances, our ODSs, is that since the kind of 1970s, when the production of these substances really ramped up, we've had, in terms of our global ozone, a reduction of, say, around 2 to 4% in that total column of ozone above us in the stratosphere, averaged across the globe. So before I go on to talk about more about the stratosphere, I thought it was also worth mentioning that ozone depleting substances, these ODSs, are also powerful greenhouse gases. So by ODSs, reminder again, I'm talking about things like CFCs. So when they're in the troposphere, which is of course where they're emitted, they're powerful greenhouse gases. So my kind of quiz question that I have for you, which is on the Menti poll, is to see if you can rank where the ODSs come compared to other well-known greenhouse gases. So I've put some other ones on there, like carbon dioxide, methane, and nitrous oxide. So I'm asking you to rank them in order of their radiative forcing. So you can think of that as the total kind of warming impact on the climate from the mid-20th century, so 1955, through to the present day, in order of high to low impact on radiative forcing. And I'll wait a little bit for a few answers to come in, and I'll show you the results. Thinking from the results, I maybe didn't phrase this question as well as I should have done. So what I'm talking about is in terms of not just the warming effect of a single molecule, but the warming effect of their concentration change over this period of 1955 to present. Let me share the results. Okay. So these are the results. So we've gone for methane being the most important ozone depleting substances, second, CO2 third, and nitrous oxide fourth. Let me go back to our presentation. This chart shows the result that I was getting at. So this is the radiative forcing of these different gases over this period from the mid-20th century through to roughly present day. So CO2 is the most important greenhouse gas. That's probably not a surprise to most of you. Maybe I didn't phrase the question too well to get at that. So CO2 is the most important greenhouse gas. But the second most important greenhouse gas terms of global radiative forcing over this period are ozone depleting substances. In fact, they've had about a third of the warming effect of carbon dioxide since the mid-20th century. And well, I guess it's good to know that maybe that's not a completely well-known fact, because I think that's was a little bit surprising to me when I heard about that. And there's this nice paper by Lorenzo Polvani and co-authors that came out earlier last year, where they did some simulations to look at this. So here I've shown two outputs from simulations that they did showing changes in Arctic sea ice. So on the left are simulations that have changes in all of these greenhouse gases. So they're trying to recreate historical trends. And so we see this loss of Arctic sea ice that's somewhat similar to the loss that's been observed in the real world. And on the right-hand side are simulations where the only thing that's been changed is the ozone depleting substances. So carbon dioxide and other greenhouse gases stay fixed, and just the ozone depleting substances change. And you can see that in that case, we still get quite a large melting of Arctic sea ice. So this is to say that ozone depleting substances are a very important greenhouse gas and should be considered in terms of understanding observed trends alongside others like carbon dioxide. Okay, so I'm going to move back to the stratosphere now and back to thinking about ozone depleting substances and their role in depleting ozone in the stratosphere. So many of you will have heard that the ozone depletion problem is the biggest problem in the Antarctic. And the reason for that is that these chemical reactions, these catalytic reactions that destroy ozone are particularly effective when they can occur on the surface of things called polar stratospheric clouds. So these clouds that, as you might guess, occur in the stratosphere, they're apparently very beautiful. Unfortunately, I've never been lucky enough to see one, but here's a picture. And they can only form when temperatures are very cold. And so in the Arctic, the stratosphere is much more disturbed because there's more land and topography in the northern hemisphere that causes the Arctic stratosphere to be more disturbed, and the temperatures are generally warmer. But in the Antarctic, where the stratosphere is less disturbed, you get colder temperatures and more of these polar stratospheric clouds. And that's why there's more ozone depletion happens over the South Pole than the North Pole. And the seasonal timing of this ozone hole comes in the Southern Hemisphere spring, which is kind of September to November time. And that's because these reactions require not just the cold temperatures for our polar stratospheric clouds, but also sunlight. So the time of year where you get the combination of both those things, the cold temperatures and the sunlight, is in the spring, because in the middle of winter, you get cold temperatures, but you don't get sunlight. Okay. So I thought I'd show this kind of interesting animation that came from ECMWF, which shows the formation of the ozone hole over a long observational period. I'll just pause before the interesting stuff starts happening. So here the bluish colors show low ozone values, the reddish colors show high ozone values. And what I want you to keep your eye on is the kind of differences and similarities between years. Maybe those of you who have a keen eye might want to keep an eye on the year 2002 because something interesting happens there. But hopefully you can see some quite large differences between different years and the ozone hole forming in the September, October, November time. Maybe have a look now at the difference between 2019 and 2020 and look how different they are. Really, really large difference between these 2 years in terms of the ozone hole. So although we have this ozone hole forming every year, it doesn't look the same every year. And then I'll just rewind to the interesting thing I said happened in 2002. You might be able to see here a split in our ozone hole. And that was due to a kind of a rare event called a sudden stratospheric warming, which happened in 2002 in the Southern Hemisphere. Okay, so the question that I have for you is, there are these large differences between different years, but what is the cause of those differences? So I'll put this question up on the Menti poll, and there's a few different options. So one could be There's changes in our emissions of ozone depleting substances every year. So perhaps, one year we emit more ODSs and get more ozone depletion. Some other years we emit less and get less ozone depletion. Another option is it could be changes in atmospheric dynamics, so changes in the winds and temperatures associated with those winds. It could be volcanic eruptions, or I've had an option for something else. Okay, well, we got this one has more of a landslide victory for this on this poll. So let me just show the results. Okay, so we have a clear majority for atmospheric dynamics, which is great because we all love atmospheric dynamics. Just to illustrate the point that atmospheric dynamics is the key control of this year-to-year variability. I just mentioned this paper that's from a few years ago now, working with the Met Office seasonal prediction system, which I think is still the current Met Office seasonal prediction system, where we were making predictions of the strength of the polar vortex. So this is the strength of the winds in the Antarctic stratosphere from year to year, and found that the model did a relatively good job at predicting the strength of this polar vortex in these forecasts that were initialized at the beginning of August and looking at September to November polar vortex strength. And then from that, we could infer our ozone and also make relatively good predictions of our ozone concentrations. And this is even though the model doesn't actually include any chemistry, this was just inferred ozone based on the relationship between the dynamics and the ozone alone. And so it's really the strength of our atmospheric circulation that then impacts the temperatures, which then impacts the ability to form polar stratospheric clouds and hence impacting ozone. So the year-to-year variability is really just a function of our atmospheric dynamics. So that's year-to-year variability, but how about long-term trends? So those of you with a keen eye might have spotted in the animation I showed earlier some longer-term trends amongst the ozone. There was a paper from a couple of years ago now by Susan Solomon and co-authors, which has argued that we're beginning to see the start of the healing of the Antarctic ozone layer. And this is kind of a tricky thing to observe because there is this large natural variability. But if you take account of that natural variability and take account of other things like volcanoes, so that was one of the options, and it's not a completely crazy option if anyone choose it, because volcanic eruptions can influence by emitting aerosol into the stratosphere, can influence ozone. But if you take account of that, you can see a slight positive trend in the depletion of ozone over Antarctica over recent years. So the reason that we're seeing a healing in the ozone hole, beginning to see a healing in the ozone hole, is because of the Montreal Protocol. And I'm guessing it's something that most of you will have heard of. So this is the international agreement that was signed a little over 30 years ago now, which started the phasing out of the production of ozone depleting substances. And every 4 years, there's a report which was mandated under the Montreal Protocol that discusses the current state of science with regards to ozone depletion. And so this is something I'd really recommend that you go look up if you're interested and want to learn more after this seminar, for instance. And the next one is due in 2022. I've been involved in writing the 2018 one and I think the 2022 one as well. And so we'll begin writing that soon. So the third and final question I have for you is, given the Montreal Protocol is now a little over 30 years old, when might we expect both global and Antarctic ozone levels to return to the levels of the 1960s? So that's your final Menti poll question. I'd just be interested to see what people's opinions are on this. Hopefully you can use a kind of slider to pick a date. Okay, I've got a good number of answers now. Let me show the results. Okay, so here are the results. I think there's quite a wide spread, but the averages I think are pretty close to what I'm about to show. A few people being quite pessimistic, going out to the mid 22nd century. Okay, so let me show what the answer is, at least in terms of the projections from the latest WMO report. So this figure shows the observations in red, and then the average of chemistry climate model projections from the latest WMO ozone assessment report for global ozone and Antarctic ozone. So you can see here that the projection of global ozone is to recover slightly faster than in the Antarctic, which will take a bit longer because ozone is more has been more depleted there. So we expect a recovery by about 2060 or so for global ozone, and about 2090 or so for Antarctic ozone. And this, just a slight aside here, that this recovery should actually happen a bit faster because of changes in the stratospheric circulation that are associated with global warming. So we expect the circulation, which brings air from the tropics to the poles, to increase, and that will actually help decrease the CFC or the ODS concentrations in the stratosphere faster than they would otherwise. Okay, so that's it for the Mentipole for now. If you're interested in the Montreal Protocol, and particularly any parents out there who might be looking for homeschooling ideas, I'd really recommend going to the UN Ozone Secretariat website, where they have this new animated, there's a short animated film and a computer game, which is apparently going to be released later this month, set in a dystopian world where the Montreal Protocol didn't exist and the ozone layer is severely depleted, and you have to do stuff to save it. So you can learn more about the Montreal Protocol there. I should say it's not all positive news with regards to the Montreal Protocol. We've actually seen in recent years the first kind of evidence for violations of the Montreal Protocol. So this figure on the left shows in green is a reported production of CFC11, one of the main ozone depleting substances. And the black and red bars show concentrations. Now they're higher than production because even if you stop producing, you still have these reserves of CFCs in fridges and cans that have already been produced. But the grey line here shows what should have happened to the concentrations given the production. But you can see that the red and black lines are above that grey line. So there's been some extra production that's not been reported. And Matt Rigby and co-authors at University of Bristol did some nice atmospheric trajectory work to kind of work out where these emissions had come from, and they narrowed it down to Eastern China. And I think they might have even identified kind of what factories were responsible for this now. So it's still something we need to stay completely on top of. Okay, so I'm now going to move on a bit to talk about the impact of ozone depletion on climate and some of the work that I've done fairly recently. And I was fortunate in a lot of this work to be part of a collaboration when I was a postdoc at Johns Hopkins University, and then continued while I was at University of Bristol, which was looking at this problem of ozone and climate. And it's a really interesting problem because it couples together atmospheric chemistry, atmospheric dynamics, and oceanography, which we'll get onto. And so I've highlighted a few of the senior people involved in this collaboration here. There's me, and some of you might know Yavor Kostov, who's a postdoc at Exeter as well, who's also involved in this project. And so this was a picture from our final meeting of this collaboration in November 2019. I think it was one of the last in-person meetings that I went to. It was actually the first time that I'd heard of this new thing called Zoom. We had some people joining us on Zoom. And there's a website which you could check out if you want to learn more about the other results from this project. Lots of other things besides what I'm going to talk about just now. So one of the motivations for looking at the influence of ozone depletion on the troposphere and on the Southern Ocean was the fact that observed trends in the Southern Ocean have been quite unusual. So what I've shown on the left here is surface air temperature trends over 1980 to 2016 from the NASA GSI dataset. And so you can see warming over much of the globe, amplification of that warming in the Arctic. But around the Southern Ocean, you can see a region of negative trends or very small trends or negative trends, showing a cooling. And along with that, we've had an expansion in sea ice around a lot of Antarctica. So this is similarly showing sea ice trends around Antarctica. And apart from along the Western Antarctic Peninsula, there's been an expansion of sea ice around much of Antarctica. There was a recent paper by Ray Chumke, which argued as well that this sea ice expansion is not consistent with being purely internal variability. And so we wanted to try and understand whether ozone depletion may have played any role in these kind of slightly unusual trends that have been seen. Just to dive a little deeper on these Antarctic sea ice trends, here's a time series of total sea ice extent around Antarctica beginning from 1980. So you can see there was a gradual positive trend from 1980 through to 2000. And that trend accelerated over the 2000s decade or through to around 2014 or so. And then this is when the proposal that I was a postdoc on got funded. And this is what happened to the trends after our proposal began. So we were trying to understand this long-term increase in sea ice, and we can see there was then a fairly rapid decline. I'll get on to it in a bit later on, seeing if we can understand this decline as well, and any potential role for ozone depletion in that. Yes, so our question was, has ozone played a role in these observed trends? So I'm going to begin by talking about the troposphere, and then we'll work our way down to the ocean. So to begin with, I'm just showing a plot from a simulation of a single model. This is a GFDL system model. And the black contours here show the climatology of zonal mean temperature in the atmosphere from the surface through to the stratosphere, which starts around about 200 hectopascals here, and upwards through the stratosphere. And this is averaged over October to January. And then the colors show the difference between a simulation with an ozone hole and a simulation with a pre-industrial conditions, so no ozone hole. So we can see that by introducing an ozone hole in our simulations, we essentially cool our stratosphere, our lower stratosphere where the ozone is, over Antarctica. And that makes sense because ozone absorbs UV radiation, and by absorbing the UV radiation, it warms the atmosphere around it. So if we get rid of ozone, we cool the stratosphere. So now what I'm showing is our mean zonal winds, so our east-west winds, averaged slightly later because there's a slight delay in the subsequent impact on winds from temperature change. So what you can see most prominently is an increase in the strength of our mean zonal winds in the southern hemisphere stratosphere. And that makes sense because of thermal wind balance, which is a relation which ties together the meridionals, north-south gradient in the temperature to the vertical gradient in the zonal winds. So we've increased our meridional temperature gradient, our dt by dy. So we increase our du by dz, so we get our winds increasing with altitude above where we have this cooling. What's perhaps less kind of obvious is that at the same time we get this dipole down in the troposphere, so the red next to the blue here, and that indicates a polewards shift, a southwards shift in our jet, our region of the strongest winds in the southern hemisphere. And this shift in the jet, this poleward shift in the jet caused by ozone depletion, is a robust feature across lots of different models. So we looked at this in a range of different models with different background states, some with coupled oceans, some run as just an atmosphere only, some including coupled chemistry as well. And you can see that the jet shift is very consistent amongst these models, for a given polar cooling. So you get on average about 0.2 degrees of shift of our jet in the southern hemisphere per degree of cooling of the stratosphere over Antarctica. Okay, so we know that ozone depletion causes a poleward shift in the jet, and I won't talk about this here, but we've also observed a poleward shift in the jet and think that ozone depletion is likely to be a major cause of that. How does this impact the ocean? So we weren't the first to look at this at all. There have been other studies that have looked at the possible impact of ozone depletion or poleward shifting of the jet stream on sea surface temperature. So here I've shown results from two different papers using different approaches to look at this. So on the left is a paper which looked at the regression of the interannual relationship between sea surface temperature and something called the Southern Annular Mode Index, which you can think of as just being an index of the jet latitude. So it's positive when the jet shifts polewards. And so this shows that when the Southern Annular Mode is positive, so the jet shift polewards, we get a cooling around Antarctica. So this ring of blue sea surface temperatures around Antarctica. On the other hand, other simulations have done long simulations with an ozone hole and without an ozone hole, similar to the plots I showed earlier, and taken the difference of those. So this is what happens in a particular model if you do this ozone depletion minus pre-industrial of sea surface temperatures. And what they show is that there's a warming around Antarctica. So these two different approaches, one which is looking at the interannual relationship, one which is looking at the equilibrium or long-term relationship, give an answer which is opposite in sign. And there's not just these two studies, there are several other studies which use these approaches, and they gave consistently different answers. So to try and resolve this discrepancy, we took an approach that might be familiar to a lot of you who maybe do more climate sensitivity type work, which is to look at the response of the system to a step change in forcing. And so we're not looking either at the short-term response, or the equilibrium response, but by doing the step response, we can kind of sample all timescales of our response. So here I've illustrated a step change in forcing, which is going to be an instantaneous ozone hole that we will introduce. And we'll get some response, which we'll call our climate response function. Now, this is particularly useful because if we take the derivative of our step response, we get a delta function, a spike like this, and therefore the derivative of our climate response function is a Green's function. And so that means that once we know a Green's function, we can infer the response to any arbitrary time-varying forcing, assuming that the system is linear, which is a big assumption, but I can talk about that more if anyone's interested about that assumption. It turns out to be relatively good. So I'm just going to show what the response is for a single model, and then I'll discuss kind of physically why the response looks like it is. So this is the response of ocean temperature as a function of depth in the ocean and time since from our sudden ozone hole, from our step change in ozone. So this is years since ozone depletion was imposed in the model. And so what you'll see is right at the surface, for the first 25 years or so, we get a cooling, and this is above this black line here, which is the summer mixed layer, this cooling stays above the mixed layer. And this, it turns out, looks a lot like this interannual relationship. So this cooling that we saw was associated with the poleward shift of the jet, the positive send up to the annular mode. But at the same time, we get this warming at depth below the mixed layer, and that warming increases with time. And after about 25 years or so, this warming kind of reaches through to the surface, and we see a warming of the sea surface temperature. And this warming looks a lot like the long-term equilibrium response that other studies had found. So, why do we get this response dynamically? When we ozone depletion, this is our wind stress response. Don't worry too much about the different lines here. Those are just slightly different simulations. Focus on the overall structure. Sorry. What you'll see is there's an increase in wind stress over the Southern Ocean as the jets shifted polewards over the Southern Ocean. A slight decrease at more equatorward latitudes. And what this increase in the wind stress over the Southern Ocean does is drive an overturning circulation. So here I've shown in the black lines, these are streamlines showing the circulation that I've illustrated with the arrows here. And the colored contours behind them show the background temperatures in the Southern Ocean. And the arrow and cross at the top show the direction of the wind stress. So here we have a positive wind stress over the Southern Ocean here. So what this is what's called an Ekman current, pushing water at the surface equatorwards. So it's bringing cold water from near Antarctica and pushing it equatorwards. But at the same time, there's also water being brought up from depth. And in the Southern Ocean, unlike much of the rest of the ocean, it gets warmer as you go down. So the stratification is due to salinity rather than temperature in the Southern Ocean. And so this upwelling actually brings up warm water from below. So this mechanism helps to illustrate why we get this 2 timescale response, a cooling followed by a warming. This was also shown in a paper by David Ferreira, looking using a different model, this diagram which illustrates this. So you can hopefully see at the surface, we get an initial pushing of our water near Antarctica further equatorwards. So that spreads our cooling, so we get an initial cooling response due to this Ekman advection, this short-term response. But the upwelling, which over time builds up and eventually comes through to the surface, drives our long-term warming response after some period of time. So far, I'd only shown results. My internet's kind of a bit slow. Okay, I think my internet might have dropped off a bit then. Can people still hear me at all?
We can hear you.
Okay, cool. I'll turn my video off. It might help. Okay, great, thanks. So what I've shown on the left here is the response of various different models where I'm looking at sea surface temperature as a function of years following our step change in ozone depletion. And the purple line is the model that I showed previously. So this is this cooling that turns into a warming after about 25 years or so. And the other lines are various different models. This orange line is the same model where I changed a particular parameterization. But you can see that all the models do give a cooling followed by a warming to some extent, but the timescale of that varies a lot. These lines are also quite wiggly because there's a lot of internal variability that goes on. Now, I mentioned once we understand our climate response function, we can infer the response to an arbitrary time varying forcing through convolving it. And so that's what I've done on the right here. So this is now looking at the response of sea surface temperature to a realistic change in ozone over time. So now, instead of years following ozone depletion, this is time along the x-axis. So this is the effect on sea surface temperatures of ozone depletion in these different models. So you can see that the models actually differ as to the sign of the response, right? So some models, the NCAR model, for instance, gives a warming. Other models, the IPSL model, give a cooling. So there's a hint that maybe some models could have, in some models, this ozone depletion may have caused a cooling that's similar to what we observe in the real world. And in fact, in some models, this cooling may over time change to a warming, not due to a change in ozone necessarily, but due to this 2 timescale nature of the response. And so perhaps this sea ice increase that's been followed by a relatively quick decline in recent years could all be part of this same 2 timescale response. However, I'm not confident enough to say that that's the case by any means. We have such large uncertainty amongst models as to this that I think a lot more work is needed to really nail down what the response looks like in the real world. We have some ideas about what the differences between models might be caused by, and I won't go into that here, but I think it's in large part due to the differences in the basic state of the ocean, in particular their stratification. And Yavel Kostov's done some nice work looking at that as well, I should mention. Okay, so to wrap up, hopefully I've shown that stratospheric ozone depletion is an important environmental issue, and that's going to remain important through to the end of this century at least. And it has major impacts not just on the Earth's radiative budget and UV, but on atmospheric and ocean dynamics. And it might have played an important role in recent trends in the Southern Ocean. I also think that studying ozone depletion is a kind of unique opportunity to learn more about the climate system, because we're seeing the climate system both respond and recover to a fairly large transient forcing. And so we can learn a lot about the climate's behavior that maybe we couldn't get from looking at a forcing like CO2, which is just a kind of a monotonic increase. And maybe we don't see the kind of timescales of the climate system as well by looking at that. So here's a few papers that I mentioned along the way, and probably most importantly, here's the link to this UN ozone game if you're interested. So that's all, and I'm very happy to take any questions if anyone has any. I'll try to pick my video back on.
Oh, thank you, Will. That was a really interesting talk. Thank you. Virtual round of applause. If anyone's got any questions, feel free to put your hand up, put anything in the chat, and yeah, we'll pass on to it. So the floor is yours, guys. Any questions? Yep, one from Adam.
Hi, Will. Can you hear me?
Yeah, I can hear you, Adam.
That was a really nice talk, thanks. And I wasn't familiar with this mechanism of the 2 timescales in the Antarctic Ocean. That's fascinating. The reason I'm particularly interested in that is that it's a signal that we see a lot in decadal forecasts. And just as you showed in your graph, where there's quite a diversity of responses in the models, so some of them show this sort of initial cooling and then warming, and others just go sort of more or less to warming. We see that in the decadal forecast. So I'm wondering if it's the same thing, and it's suggesting to me I need to check with what people are putting in for the ozone in the decadal forecast, because you know, that community is probably more interested in the other greenhouse gases rather than the ozone per se. So I think that's a really interesting thing, and I just wondered if anybody is looking at the reanalysis for the ocean to try and detect whether or not we've passed this point where it's going to flip to warming. At the moment, I think, as you pointed out, there's been quite a lot of cooling around Antarctica, but given the recent decline, is there any ocean analysis showing that it's now changed to be pulling up the warm water?
Yeah, it's a good question. I think we should be learning a lot more about that, as there's been a targeted release of I can't remember what they're called. There's Argo flakes, which are essentially more designed for the Southern Ocean, include some more biogeochemistry sensors. There's been a lot of release of those recently. There might be some more information about recent circulation trends.
Be an interesting piece of work, wouldn't it, to see if you can detect whether that point's been passed or not. Yeah. Anyway, thanks again. It's a great talk.
Thanks,
I think the next question was Guy, and then we'll go to Tim.
Hi, thanks, Deneen. Yeah, thank you. Well, really interesting. Not something I know much about. This might be a bit of a naive question for climate scientists in the room, but I'm interested in the kind of the dynamic. There's these two different impacts on the climate that ozone depleting substances have. There's a sort of a direct one of the greenhouse gas themselves, trapping infrared radiation, and then there's this sort of secondary or indirect effect on their interaction with ozone. Do you kind of have a sense of how those two, the sizes of those two effects compare, and if one of those sort of might persist longer than the other, or if you use anything about sort of the dynamics of those two different interactions with the warming?
Yeah, so yeah, it's a good question. There is some kind of overlap between the two effects, I suppose. So one impact of greenhouse gases, while they warm the troposphere, they also cool the stratosphere, and so by cooling the stratosphere, you make it slightly more favourable for these polar stratospheric clouds to occur, and for ozone depletion to happen. So there is a slight kind of overlap in that sense, but it doesn't really work the other way so much, in that changes in stratospheric ozone, the radiative forcing for changes in stratospheric ozone is very small, so it's not really something you need to worry about in terms of climate change. It's quite a popular skeptic argument for some reason that climate change is due to changes in stratospheric ozone, but the radiative forcing is very small for changes in stratospheric ozone.
All right, thank you.
Yep.
Okay, Tim.
Oh, thanks, Deneen. Yeah, lovely talk, Will. My question's really about the implications for the ice sheets, because my glaciologist friends and colleagues have been highlighting how the accelerated retreat of parts of the West Antarctic ice sheet and parts of the East Antarctic ice sheet, the bits that are marine grounded, with retreating grounding lines, are super sensitive to the ocean temperature and appear to be responding to a noticeable warming of the ocean temperatures impinging on the ice sheet underwater. And I'm just sat here wondering, could that be attributed at least partly to what you showed, which is this, or does your model already show that you're getting a shifting of warmer water right up against the ice sheet, or does it not resolve that one enough?
Yeah, so that's not, we haven't been able to resolve things on quite such a small scale, including the ice shelves. There has been some work showing that, so although I was talking about the jet shifting polewards and the westerly winds over the Southern Ocean, around the coast of Antarctica, there are easterly winds, and if you think about the kind of Ekman effect of those, they're thought to be important in kind of pushing water under the ice shelves, I think. And if think an increase in those associated with a poleward shift might also be expected. So there are like physical reasons to think that that could be related to more warm water being collected under the ice shelves. I'm actually a co-supervisor of a PhD student at Bristol who's doing some regional modelling to try and look at this as well. So
cool.
The kind of thing that you need a more of a regional approach to really resolve. The currents are so complex under ice shelves.
If you could show that, it would be a really nice, well, an interesting Earth system kind of story, that the ozone depletion might have been the crucial thing that's playing a role in what some of us think is a bit of the West Antarctic ice sheet's already past the tipping point of irreversible grounding line retreat, thanks to fairly subtle warming in the Amundsen Sea embayment. Great.
Okay, last Timothy.
Hi, yes, Tim Malone here. Just a quick question. Well, can you bring us up to date on what's happened about the Eastern China and the sort of breaking of the Montreal Protocol? Because in fact, it's quite a significant amount of sort of ozone depleting gases that were released. I mean, it wasn't just a sort of accidental thing. It obviously was going on over a period of time. Can you tell us what happened since then and what the response has been?
I unfortunately I should be more up to date on this than I am really. I'm not the expert on that, I'm afraid. I think that the production, I remember it was largely tracked down to some kind of like foam production, I think, in
That's right,
and some individual factories were found responsible. But I think there was also something in the news very recently about, like, as in a few days ago, that I haven't fully read up on, but about some other rogue emissions that have been found as well. I don't know if anyone's read more about that than I have, but yeah, I think there's been some new, I think including emissions from Europe as well in this most recent study.
So does the protocol have teeth? I mean, are there consequences that countries have to, apart from being sort of shown up and caught out?
Yeah, I don't know. I would imagine that it does. Yeah, yeah. Maybe someone else knows more about it than I do. Yeah, I should hope it does. I know that the authors who did the trajectory study to show where the emissions had come from, coming from northeast China, were not particularly popular with a lot of the Chinese government at the time, at least.
Thank you.
Okay, and then the final question will go to Matt.
Hi, I had a quick question about the poleward shifting of the jet and the response in the ocean. I was just wondering, because CO2 forcing is also associated with the poleward shift of the jet, and I was just wondering if there's a similar mechanism that might go on in the ocean there with the delayed warming. Yeah,
absolutely. Yeah. So CO2 also causes a poleward shift in the jet. Over the kind of historical period, say from the kind of mid 20th century through to present, we think that ozone is the predominant cause of the observed shift in the jet, and well, the CO2 has had a relatively small impact compared to ozone. But as ozone recovers and CO2 continues to increase, then these two effects will kind of cancel each other out to some extent, because the ozone recovery will be driving the jet equatorwards and the CO2 increase will be driving it polewards. So exactly how those two play out against each other is, I guess, fairly uncertain. But yeah, I certainly think that the mechanism itself would apply whether or not the forcing is ozone or CO2, this kind of 2 timescale response.
Interesting, thanks.
Brilliant. Okay, we might wrap up here then. We're just approaching the end of time. Thank you again, Will. I'll just stop the recording now and we're sharing.